Yeah. Um, so visualization. Couple things I want to note before we dive off. There's a lot of useful Python libraries out there for doing data visualizations. And I don't think anyone would argue with us that one of the most fundamental ones is Matplotlib. Been around a long time. And when Python was gaining traction in the software ecosystem, there were a lot of people coming over from MATLAB. And so Matplotlib really kind of emulates a lot of the features and stylistic choices of MATLAB. And so that's why I think it had early precedence. I still think it's a really great starting point. And whenever I do data explorative data analysis in my notebooks, I start with Matplotlib. At the end of this notebook, and when I do move the answer key into the Google Drive, I have dedicated at the end several cells to another library called Plotly. And Plotly is really nice too. And we're not going to go through kind of hands-on Plotly in this session due to time, but I do have some blocks for you to explore on your own. And I think one of the reasons Plotly is so nice is it has a component, a sister library called Dash that allows you to create a Python server and host your visualizations in the web browser. So there are a lot of organizations. I've talked to a lot of colleagues who came out of the chemie department are now working as engineers with data science chops at their organizations who use Dash to create their visualizations to share with other people in their organization or stakeholders that they work with. So it's also a great library, but we just make minor reference to that at the end. Okay, so the actual submodule that we use out of Matplotlib is called pyplot. And what we typically do is we import matplotlib.pyplot as PLT. Everywhere you go, it's the namespace that we utilize is PLT. And it's pretty simple to use. The standard way we use Plotly is to create two separate objects, a figure and an axis. And I'll talk more about that in a second, but I want to show you how simple it is to just operate within the Plotly namespace. So in this case, I've got a series of X values, a series of Y values, happen to be the Fibonacci sequence, and I can plot them with plt.plot X and Y. And you'll notice there's, it prints out a line. There are no markers shown by default. There are no grid lines shown by default. It does have major tick marks on both of our axes. And there is some intelligence here in the interval that it displays on the axes. You'll notice that on the left in the y-axis, we have 2, 4, 6, 8, 10, 12. Whereas on the x-axis, we have 1, 2, 3, 4, 5, 6, 7. So it's automatically sort of detecting our intervals and sort of intelligently applying our axis labels is kind of nice. Some of the very first attributes of our plot that we'll want to introduce are the title attribute and the X and Y label. So in this cell, I'm going to recreate the same exact plot. Notice just this time, I've fed the X and Y values directly into, actually, let me show you this. So let's do plt.plot, right? Since we're opening up and typing it out, we can see the tooltip pop up and it tells us where our, what do you call them, parameters are in the function. So the first parameter is X, the second is Y. We'll get into the other keyword arguments here in a minute. But so I'm just directly putting in my X and Y list in this case. And then once I have that object established, I can do plot.title. You see my title appear here at the top. Plot.x label, I just gave it the name order in sequence. And my Y label is value, just the Fibonacci value for that place in the Fibonacci sequence. So I already mentioned some of these things. What do we think about this style? We see, the X and Y axes have auto generation of their tick marks that are kind of pseudo smart. Does anybody recognize this color that we have as our default color? Beyond just being blue, does anybody recognize this particular blue? Colors.
Is it Python blue?
Okay, it's part of the Tableau 20. I don't know if you can call this. I don't know Python blue. Maybe Python does also adopt and call the Tableau colors the Python blue color. I'm not sure, but this is blue from the Tableau 20. So Tableau, they're headquartered in Seattle, right? It started in Seattle. Pretty sure they're out in Ballard,
Fremont.
right by Google. Fremont.
Oh.
Fremont. Yeah, so they've done a lot of research on the optimum colors, and we'll visit those further down in the notebook. But they've done a lot of research on how to distinguish, to arrange colors far apart in the color spectrum, but also make them pleasing, make them so that they don't, what do you call it? So that they're not a problem for people who don't see certain colors and that sort of thing. Okay, so we've just so far been operating in the PLT namespace. We haven't directly declared the objects I mentioned earlier, which were the figure and the axes objects, but now we're going to go ahead and do that. So typically when we do this, I'm going to start with just first declaring the figure. And we see the output here is figure size 432 by 288. So we see there's some default pixel value size of our figure with 0 axes. There's no axes attached to our figure. I'm gonna add this line. So notice we haven't covered objects yet in these tutorials. But don't worry, we're not going to get too deep into that. We're only going to talk about these two today. So all you need to know is that a lot of these methods, we call them sort of blueprints for creating objects in Python. So for instance, the example we saw yesterday for this was Dave mentioned, what was it? Range, right, Dave? Range 10, right? And he gave the example of range 1,000,000, right? And so that is an example of it's giving a blueprint for creating an object structure. And then once we list it out, it creates the actual object itself, which is a list from 0 to just below 1,000,000. And in this case, plot.figure is the blueprint of creating a figure object. Once we actually declare it and assign it to a variable, we now have that object. And that object inherits all of the methods and attributes that were within that plot.figure function or class. And so one of them is add subplot. And so once we have our figure, we access that function, add subplot, like so, and we create a new object with it called AX. And this is just standard practice for operating within matplotlib. You create a figure, and then you create an axis that's a part of that figure. So I did this in 2 separate lines. The way I typically like to do it is to do it in 1 line. And so this is what I'm doing in this cell here. I'm saying figure, comma, axes, plot.subplots. Let's just take away the rest of this for a moment and see what this does. So we see versus up above when we just said figure equals plot.figure, we just saw that there was a return carriage or a return at the bottom of our cell that said, oh, hey, there's a figure here. It doesn't have any axes attached to it. Instead of that, we now have displayed a figure with an axes object in it. And you know that because you see the typical graph output that we associate with a figure in our minds. I'm gonna go ahead and use the tooltip here. So these first 2 parameters that I put into plot.subplots were the number of rows and the number of columns to put into the figure. So I'll explore that later when we talk about subplots, but for now, we're just going to set those equal to 1. And so when I do this, I get 1 axis. And if you notice in the tooltip, the default value for these are 1. So the default behavior of plot.subplots is to return one figure with 1 axis object. The second most likely parameter you're going to use with plot.subplots is the figure size. So I'm going to go ahead and put this in here, and let's make it 5 by 5. Excuse me. Might be figure size, not fig size. Okay, no, it's fig size. So fig size equals open parentheses 5 comma 5 close parentheses. I'm not sure. Did we talk about tuples? We did not talk about tuples. You don't have to know a lot about tuples either, except that they're very much like a list. The word that you'll hear to describe tuples is that they are immutable. So once you declare a tuple, you cannot change them like you can a list. It's kind of just the only difference you need to know about right now. And it just so happens that fig size takes a tuple as its input. The first value is, well, let's test it. I can't remember if it's X or Y. So let's change it to 10. It's X. The first value is the width of our figure in inches. And the second value is the height of our figure in inches. This is like a really technical way to start us off, but it'll give us a framework when we go and do more fun things later on. So just to recap, we have a figure. We declare our figure object, which you can think of as like a blank canvas, kind of similar to like a JavaScript canvas. It's what we're going to put all of our things onto. We can declare certain things like the border of our figure, the overall size of our figure, and then within there, we attach our axes objects, which are the typical graphs that you imagine when you talk about a plot. So a figure will have anywhere from one to many axes as a part of it. And then within an axis, you have the axis, the X and Y, or in some cases, Z axis, depending on if you're doing 2-dimensional or 3-dimensional plotting. So that's kind of the taxonomy of a matplotlib figure. And it doesn't get any more complicated than that in terms of its components. And then in this example here, I'm just showing, this is my favorite way, and it's a very succinct way to declare your figure and axis in one line of code. Fig, comma, ax equals plot.subplots. The naming conventions for your figure and axis is typically fig and ax, but people can name them whatever they like. But this is somewhat typical. So I want us to just pause and take a moment here to, in this cell, practice declaring a figure and axis object. And I think in most of these exercises, I give you the components to complete the exercise. So if you're trying to think and remember, hey, what code cell should I look back on? You can look here in the plotting building blocks, or in the building blocks with bullet points section of these exercises, and kind of tease out what we're looking for. I'm going to go ahead and take a break for about a minute. And if there are any questions. Remember that when you start typing, you can use the Colab tooltip to do things like see what parameters you have available to you in the function. The B bonus on this, we kind of touched on yesterday. There was a question about reversing a list. I'll talk about that in just a second. Okay, I'm gonna go ahead and type this out. We got fig, comma, ax is equal to plt.subplots. Number of rows, number of columns. I'm gonna go ahead and say 1 and 1. And see if I don't remember what this keyword is to make the size. Can I find out going through here? I don't actually know. Maybe in the examples? I didn't realize they had so many examples in this tooltip. Nice. I'll see if I think I remember now. Fig size equals, and then what was it? 6 inches width. So I'm gonna put that number first. 3 inches tall. See what that does. Okay. All right. I've got my figure, and now I'm gonna do. I need to access my axes, which was AX. I called it AX. I'm gonna do AX dot plot, and then X and Y.
I have a question for you, Wes. Could you have decide to plot, let's say, like the first 3 elements using one of Dave's slicing that he introduced yesterday?
Yes. Let's play with slicing. Okay, this is great. So Stephanie, actually, Stephanie, I don't care what you said. I'm going to assume what you said and answer my assumption of what you said. But I think I got it right. So I think
Good.
Stephanie is talking about.
I just meant like a range from that list, pretty much.
Yeah. Okay. Let's do that.
Yeah.
Let's do the first 3 values. So let's do 0 to 3, right? The index starts at 0, 0, 1, 2. I think the 3 is exclusive, so I'm going to try 3 and see if it works. And I need to do it for both of them, my x and my y's. 0, 1, 2. So that's the first 3 values. So I thought Stephanie was talking about steps. So let's do that because that's fun, and that'll help us understand why : -1 reverses our order. So when you're slicing, you can put in a second colon, and anything after that is your step size from the slice. So let's say I just wanted to get the even values of my Fibonacci sequence. I can do that like so. Excuse me, is that the even or the odd? Well, I don't understand because it starts at 0.
I think it'll still be like it'll iterate by 2, right? So
yeah, so it's a step size of 2. So it's every other value and it starts at 0.
So it's, yeah, so you'll have.
Or the 0th position. So I should see 1, 2, 5, and 13. And that's what in that y-axis, and that's what I see. If I wanted to do the odds, I'd start on 1, right? And now I get, now I get 1, 2, and 5. And 8? No. 1, 3, and 8. 1, 3, and 8. Yeah. Which are the evens. This just depends on if you're talking about indexing by Python or indexing by the X array, right? But you get the idea. For reversing the order, I'm not going to do anything to X because I want X to still be my 1, 2, 3, 4, 5, 6, 7. And now I just want to plot descending in Fibonacci. So what I'm going to do is : and then I'm going to make my step -1. And so now I've reversed that Y list so that I'm going from 13 to 1 instead of 1 to 13. Actually, when I started learning Python, I didn't pick up on this trick with slicing until I had been using it for some time. And then somebody in my research group used it during group meeting one time, and I thought it was pure wizardry. So you can sidestep a lot of code knowing how to like manipulate arrays or lists in this fashion. Any questions? All right. Now we're going to play with some of the basic attributes of our axes. They are the markers that we can style with, and then the markers that we use, that is the actual data points, or the way the data points appear on the plot, the way the lines appear on the plot, and the color of the lines and markers. So you have a whole ton of markers to choose from. There's something wrong with this list. In our next exercise, we're going to play around with this. Some of them don't work in this version of matplotlib that we have in Colab. I don't know if there are other versions that make these all available, but anyway, there's quite a few markers to choose from in any case. Quite a few different kinds of lines to choose from, and there are some base Python colors here. The way I generated these lists was through importing this importing matplotlib and then accessing the markers, lines, and color banks of matplotlib, and I printed those lists out. So let us start with, what do I want to do? Let's start with this. It's going to like show, so we haven't actually plotted two separate things in the same, two separate sequences in the same axes yet. So I want to just start with what this looks like out of the box. Maybe my commenting this out isn't the sexiest, but that's okay. There's also another difference here from what we looked at earlier. Remember earlier, when I was talking about title, X label, and Y label, I did the following. I did plot.plot, and let's just, I don't know, 1, 2, 3, and 4, 5, 6, right? And then I did plot.title, and I had a title, and then I did the same thing with X and Y, right? Well, if you'll notice, what I've done down here is a little bit different because I've gone through the more astute practice of actually defining my figure and axis objects. I'm now doing something a little differently. I'm accessing my axis object, and instead of saying .title, I'm saying .setTitle. Same with X label and Y label. So I have to remember this when you're actually accessing the object. Some of the namespace is going to be a little different than if you were to directly operate within the pyplot namespace. Just something to note. I think if you get in the habit of just doing it one way each time, you won't really even think about it. Also get in the habit of doing tab completion, because then you'll know if you're on the right track or not. Like if I was to try to do ax.title here, I'd get an error. But look at this error message, kind of interesting, right? It says text object is not callable. What does that mean? What does that mean? I don't know. I can explore that. Ax.title. It's an actual thing. It's not a method. It's an attribute of my object, right? So the namespace changed a little bit because I actually have an object with a title now. It's no longer a function. So they had to change what the function is called for the established object. So this is what our colors look like out of the box when we're just adding additional lines to the same axes, right? We have ax.plot. We use we have our Fibonacci sequence plotted here. And then I just plotted a random string of values with the same X values to the same axes. And look, our colors automatically changed. It's another kind of nice feature of matplotlib out of the box. This color, this orange, is the Tableau orange. All right, I'm going to get rid of my second line completely here. Okay, so we're back to our familiar single sequence of data plot. I'm going to start playing with these values now. Marker, line style, and color. So I chose an up caret, and that makes an upward pointed triangle. I can make a dashed line by using dash dash. And then I can select what the default color was, blue, by doing tab blue. This is kind of a nice feature of matplotlib, is you have direct access to the Tableau colors by using tab :blue. What else do we notice about these parameters? They're all strings, right? So marker, line style, color, if we're remembering our data types from earlier in the week, these are all string inputs. So I'm going to go out on a limb here and not reference that little cheat sheet above and just play with a few different things. So if I do a greater than sign, I get a right facing triangle, less than sign, left facing triangle. If I do the number 8, I get what should be an octagon. I can't really see. Oof. I just zoomed in a lot. Kind of looks like a circle, but I'm pretty sure it's an octagon. Now I'm too small. Okay. I don't know if the other numbers work. 7 doesn't work. Or 6. I think 5 will give me a pentagon. No, it doesn't. I know S will give me square. So, you know, there's some things that you have available and some you don't. Let's see, line style. I think another one I have is a colon dash. No, dash period. Yeah, dash period. So that's like a long short dash. And there's a whole host of these. And, you know, for those of us who are kind of having to crunch through figures quite a bit, like if you're planning on doing research and you're having to generate plots of your data, what can be useful is to create a for loop that cycles through these different line styles when you're plotting different kinds of data so that it just automatically differentiates your data in your thing, in your axes, precision of language. All right. Let's say I'm satisfied with that. I'm going to go ahead and add in my other data sequence here, my random numbers, and I'm going to think about why this is not working. Unexpected indent. Oh, I'll put this. Oh, right. I have this parentheses. Okay. Okay. With the second line, you notice I'm not using my tab string trick. I'm actually putting in a hex value. So if you go to like, I don't know, you go maybe to Google and be like colors by hex value, hex code. There's probably some like things on the internet you can use to like, yeah, just like whatever color you want. Let's say I like, is that hashtag is hex, right? I don't know, I don't remember. Just gonna grab that, put it in here. Boom. Should be like that. Ooh, is that what that looked like? Oh, I guess it was just kind of this dark brown. Okay, so you can make these any color you want pretty easily. Last note, just to reiterate, when we set the title and labels, we use the set prefix once we've declared our axis object. Okay, versus when we operate directly in the pyplot namespace. Oh, and something that's non-intuitive. If I don't want any lines, which we often don't want any lines because, you know, a line insinuates there's some meaning behind it. Like we're assuming there's some relationship. We're not always trying to make that point when we plot data, right? To make a scatter plot without any lines, you just set the line style to an empty string. That actually is much more pleasing to the eye. That was bothering me seeing like the Fibonacci sequence by lines for just the first 8 points or so. Yep. Lines are just, you know, you go through early education and you're like, lines are the best. And then you further you get in, you realize there's a lot of insinuation when you put a line. Don't always want them. Okay, so here I've included the hex codes for the tableau 20. They look, I don't know, they look a little weird to me in this picture. I think it's a little off tone, but maybe that's just me. I want us to take a little bit of time now to play with these input parameters. So I've got a code block here. I went ahead and I've created random Y values. I've also started us off with the, you know, accessing the plot method of our axis object. So what we would like to do here is just declare the marker, line style, and color value for each one of these sequences of data that we're plotting. I'm going to take 2 minutes here. One last trick. You don't have to type out line style. You can just type out ls. ls equals whatever you want. I'm gonna go ahead and do this too, but I'm gonna be quiet when I do it. If you have extra time, use the tooltip. The tooltip here is just because there's so many like parameters that you can put into plot. I don't think the tooltip is like super useful, but you can play around with some of it. Like I don't like red pulse, red pluses. That's a cool. Is that a marker? Or no, it's combining. So you can combine color and marker style into one command. Nice. We're coming along the time that I said, so I'm going to stop playing with this. One cool thing that I just recognized here is you can do a marker style with a comma, and it's just like this tiny little, just like a tiny little dot. For those of us who like, what happens when we just keep, let's just keep, I don't know, change, like, I'm gonna change my values a little bit, but keep adding lines. And let's just note some of the default behavior, right, of the coloring. I don't know, I'm just gonna make some of these astronomical so that we can see the differences. So what do we notice? Well, maybe it's not obvious, but we're continuing to just cycle through the Tableau 20 is our default color cycle. All right, we're gonna move on from here. Stop me if you have questions. So now we're about to talk about, I think it'll become more obvious why we have this behavior of creating a figure or a canvas and then creating axes objects that we actually plot on. The reason for this is we would maybe like to have many different plots on the same figure or the same canvas. So this is what we're going to do next. Quick couple of notes. So to make the lists of data that I'm plotting for these examples, I'm going to use a module called random. So we haven't played with this module yet, but it has a few useful functions in it. One of them is just to generate a pseudo-random number between 0 and 1, and I'm going to use that to create some values. The second thing I'm going to do, that's a little bit new, is I'm going to use something called list comprehension to very succinctly generate lists for us to plot. I'm not going to spend too much time here on this, but you can think of list comprehension is doing the same thing as a for loop, but it's much cleaner for us to write because you can write it on one line. The caveat is it's not necessarily faster. I think actually oftentimes it's not faster, computationally speaking. I have read from someone who I think I trust that depending on the Python interpreter, it could be faster. But I've actually never seen a list comprehension be computed faster than a for loop. Anyway, I think the main driver for writing things this way is just for succinctity in the actual code when we're reading it as a person. And just here's a demonstration of two different ways to generate those random numbers and put them in a list with less comprehension and with a for loop. All right, we're going to break this down. We'll go ahead and run this cell. All right, this first line should look familiar to us. We have the familiar command plot.subplots, but now instead of having the default value of 1 and 1 for number of rows and number of columns, I've got 2 and 2. Let's actually just comment the rest of this out and see what this looks like. I generate a figure or a canvas with 4 subplots, right? 2 rows, 2 columns. Happens when I do 2 rows and 1 column. I get one stacked on top of the other, vice versa, one side by side. I can play around with fig size to make these ratios square again, right? So I think if I recall correctly, the first value here is my x and the second is my y. So I'm going to do 10, 5. Now I get 2 squares. Let's play with this a little bit more. I can do 5, 10, and then swap these values, 2 and 1. Did I just come from 2 and 1? 2 and 1. So we got 2 squares topped on one another. Change this back to the way it was. The first thing that happens when I declare my figure and axes like this is ax. What is ax? I'm going to do it this way. Do we talk about type built-in method, Dave? Do we? Okay, cool. So the type of my ax object is not an axis anymore. It's it's a numpy array. So we haven't talked about NumPy, but all we need to know about this is the way we access components within this array is very similar to list slicing. And so that's what we're going to do down in these cells. So because there are multiple axes that have been established with my plot.subplots command, instead of returning all of them, because I've only given 2 things for plot.subplots to return its objects in, it packages the axes into a NumPy array. And so now to access, this is where like language really sucks, right? To access the actual axes within AX, I have to use slicing. Okay, so that's what I'm doing here. So 0, I'm accessing the top row. 1, I'm accessing the second column, right? Indexing starting at 0. Okay, so I'm getting the top right axes. Okay, from there everything's the same. I've done this squirrely thing with list comprehension to generate some random values. That's what you see here. In fact, if I just keep running this, you'll notice all those values keep changing. That's from that list I'm generating there. Okay, I believe we talked about range yesterday. It's just giving me a list from 0 to 9. Yes, we talked about this today even. Yes, so I'm just getting a list from 0 to 9 every time. I think before everyone got into the room, I was talking about how I went through this today to try to get rid of all of my NumPy stuff, and this one just snuck past me. It found its way in here, but luckily it's not too bad. It's just, let's give an instance here. Let's go ahead and talk about a corollary with lists. So if I make a list of lists, Stephanie was typing this into the chat yesterday. Let's say I have list 1, okay? List 1 is 0, 1, 2. And list 2 is a list of list 1, okay? I'm gonna print out list 2 here. If I want to get that first list within list 2, I do 0, right? I'm indexing starting at 0. That will get me the first list. In fact, I'm just going to do this exactly so it's a little bit more exactly like what we're looking at with our AX object down below, okay? So now I have 4 objects in this list of lists, 4 objects. I'm going to grab that first list in my list of lists. All right, there it is. And now I'm going to grab the second object within that list by doing a 1, okay? It's the exact same idea here, except with an array, we don't put them in separate square brackets. They're within the same square bracket set. This level of indexing is slightly, it takes a while to get intuitive with it. So if it feels a little chunky, that's normal. But in terms of what we're trying to achieve with our subplots here, the main thing to take away is that the object that's returned here is no longer our AXES, it's an array of our AXESs. All right. Our objective in this exercise is to recreate the same kind of figures that we did above. This time, instead of a 4x4, a 2x1. And in the code block, we already have our X array, our list of X values, our list of Y values for our Fibonacci sequence, and then our random list of values generated by random.random. This will give us a chance to get comfortable with a little bit of slicing with NumPy arrays, as well as declaring our X, Y labels and our title. And we'll give us till 6:25 to play with this, 4 minutes.
If you have any questions as you're working on the exercises, just let us know. You can write to us to any of the CHAC helpers or the common chat, whatever you prefer. If you want another tone of blue like Rembrandt blue, you can also find those colors. Python is super versatile.
If you're having trouble with the indexing, something to think about is there's only one row, right? There's no longer 2 rows. So you're basically, it's exactly the same as indexing a one-dimensional list. Can I get a thumbs up, a virtual thumbs up, if you're familiar with NumPy, if you've heard of NumPy before, or like used it? Okay. I was, you know, from a pedagogy standpoint, like I was talking to someone about this today, like, it's not necessarily something that you need to have in a teaching sequence at all. Like, you can go direct, like in our case, we're going directly to Pandas because we have a very like defined data set and a very defined objective of what we're trying to do with it. The caveat is that a lot of these libraries were built on NumPy, so you find it hidden in there. What you'll find is like, for speed purposes, you want to have like the smallest, simplest data object possible whenever you're doing something. This is something that took me a long time to figure out in grad school. And I ended up doing things like writing genetic algorithms that manipulated pandas data frames, which are a lot heavier than manipulating, say, a dictionary. And so, like, despite in what sequence you learn about things, you'll always see like objects are built on the smallest things possible and built in there. So anyway, Pandas is built on NumPy. NumPy is built on these smaller data objects we talked about earlier in the week. This is how things, and then Matplotlib is built on this as well, right? So it's just interesting to see how things percolate up. I think that's the chemi word, right? Okay. All right, so this was like the real, so I rarely work with Matplotlib directly. It's a little bit clunky. You have to like type things in yourself. I almost always do my plots directly with Pandas. And so this is kind of the fun stuff. But when I first taught this visualization tutorial, I actually had this swap. I started with Pandas, did the visuals, and then showed Matplotlib. But I think it's really helpful to get like a clear understanding of what Matplot looks like by itself. So that's why we started there. So now we're going to import Pandas. We're going to import our Boston data set as we did earlier. And a little fun stuff, we're going to import IPython widgets. We'll talk about that towards the end. There's certain sections in here that I'm going to go through pretty quickly. I just want to show you that they're available to you as you go through CHAC. But in the interest of time, I'm going to just kind of make reference to them. Okay, so we've got our Boston data set loaded. We're going to declare an object with it called dataset. Go ahead and access the DESCR attribute of that to get a little printout of the variables that are in that data set. Kind of remind ourselves of what those look like. And there's a lot of ways to declare a Pandas data frame. And so I think that this is very similar to what Dave did yesterday. Actually, I think this line is exactly the same, right? So we have Pandas here as pd.dataframe. We give it the data first, and then I've got this parameter flag columns to give it the names, right? I'm calling it feature names, or I'm accessing feature names from dataset object. And actually, if we stop there and just, I don't know, just like look at it. Get out of here, tooltip. All right, I'm gonna run this. This should look like what we looked at. Look like what we looked at yesterday. Okay. This second line here that I'm doing is I'm accessing a new column of my data frame. I'm calling it target in all caps, and I'm setting its values equal to dataset.target. So I don't know if we included this yesterday. I can't remember, but today I'm including the target values in my data frame. And here we see them. They automatically just get bumped to the very end of my data frame object. There she be. All right, we're going to get rid of this. So if you're trying to delete a cell, what's useful is you control, hold it down, MD, and it'll get rid of that sucker for you. All right, just kind of looking at some basic attributes, looking at our shape, right? We got 14 columns, 506 data entries. Check our column names. We see that target appears there now. And I'm pretty sure we went over this yesterday, but one of my favorite things is df.describe. And this return will change depending on what's in your data frame. So I wonder if I can do this real quick. I'm gonna, it's not good for time, but I'm just gonna, Wes is gonna do it. All right, and then I'm gonna do equals, will this work? I don't remember. I don't know how to cast it to every row, but we're gonna see.
Just give it,
I'm gonna
it'll set every row to the string.
say it again, Evan.
If you just set it to a string, it'll set every row to the string.
Got it. Nice. All right. So now if we do this, well, where is my, Wes is going to do it. There she is. df.describe still, it just cuts it off. interesting. That wasn't the behavior I expected. That's okay.
I think because it's a
Let's try
string,
this.
it can't be broken down into count, means and standard deviations and stuff.
Yeah, well, so exactly right. So depending on what your data type is, if it's numerical or a string, you'll get these two different returns. What I was expecting was, I thought I'd seen it elsewhere, but maybe not, and it might have to do with like a majority case, like if the majority of your data is string or the majority is numbers, it might do a different return. Anyway, the point being, .describe will make different returns depending on what your data type is. So exactly what Dave was saying, in this case, it's a string, so it's just giving us the count, the top unique occurrence, frequency of that top occurrence. So anyway, I don't want to have this floating around in the rest of my examples, so I'm going to rerun these cells. Okay. So now onto plotting functionality in Pandas. We can just use data frame and then dot plot, and it'll return something that looks essentially exactly like what plot.plot looks like, right? Except now we've got this added thing because we've got multiple data entries and multiple lines, we've got a legend that fits in there. So that's cool, but how do I reconcile this with the figure axes nomenclature we just talked about? Do not fret. The way we do this is we do the same thing as we did before. We do figure axes and then plot.subplots, right? All that is there. And then when we make the call to our data frame to do the plotting, we feed it which axes to send it to. And I wasn't making this up when I said FIG, AX are common namespaces to use for your objects, because looky here, actually, and this makes it easy to remember, when I'm using pandas, the parameter that I need to feed it is AX, okay? You see that? So if I just do this, I'll get my figure up here, and then I'll get my plot down here. But if I tell my data frame which axes to append to by doing AX equals and then the name of my axes, it'll put it into that axis in the figure, okay? So there it is. And then in this next one, again, I like scatter plots. Don't really like my lines there all the time. So everything that I had access to in plot.plot is available to me within dataframe.plot. So I can set my line style to an empty string. All my lines are gone now. I think I can even shorthand this to LS. There it goes. Change my marker to a upward triangle. All right, so I'm going to give us a moment to play with this. I've done a little bit of pandas heavy lifting for this exercise. Let me walk you through my thinking here. So when I was looking at this, and maybe you notice it too, I've got a lot of values that range from 0 to 100, and then I've got some really big values. And like my, I don't know, gut instinct is I'd like to kind of just separate those out so I can kind of see what my ranges look like. So in exercise 4, what I want us to do is have one figure, 2 axes. The first axis, I want to plot all of my data that ranges from 0 to 100. And in my second axis, I want to plot all of my data that has any values associated with it that are higher than 100. I went ahead and already did this logic for determining which columns those are. Okay, so I've got a variable here named low features, which is a list of my values that are all sub 100. And then I've got a list of column names called high features whose data at least one time is higher than 100, okay? So the objective here for exercise 4 is to use those column names, populate a top and bottom axes as part of one figure. I'm going to pause for about 4 minutes.
Dave, I love your video. I totally saw it. I was like, that's Dave. I have to do one like that.
And to move my desk to standing.
Makes sense.
If you have extra time, you kind of break down that list comprehension that I have for the low and high feature list names and see if you can recreate it or convince yourself that the logic is working there. I think there's some built-in methods, Python methods that we haven't covered yet, all and any. You might be able to learn about them by doing all and then question mark. You'll get a little help thing pop up. Remember our slicing from earlier, right? Our AX object's actually gonna be an array of our axes objects, so we have to access them accordingly. I'm gonna spend another minute here. So we're not going to talk about legends today. Leave that for folks to investigate on their own. But I do want to draw our attention to some behavior here. I think where was it? When we first started with scatter plots, we noticed our legend was over here on the right. We complete this exercise, our legend position has changed. Something that's pretty cool about matplotlib is the default behavior will be to arrange your legend so that the least amount of data points are covered by the legend display. So that's pretty dope. You can take over control of that and tell it where to be placed. Actually, there is a way to have total control over axes placements within a figure. We're not going to cover that either. And to be honest, like I have used this. If you're trying to generate a lot of figures, you can find yourself in a space where you're getting really into the nitty gritty. And it's like if you're crunching out a lot of figures and trying to iterate through a lot, you can be oftentimes much better off just adhering to the subplots nomenclature and trying to stick to this column row scheme. The actual method I'm thinking about is called grid spec. And so you have precise arrangement over where everything is, but if you're creating a bunch of for loops to plot a bunch of data and make separate figures and stuff, it can get real messy. So anyway, we should have gotten here. We have in our top plot, everything below 100, and in our bottom plot, anything that had at least one data point that went above 100 in value. So just kind of like take advantage of two different Y scales to see our data. All right, these sections I'm going to go move through a little quickly, so we have a little bit more time dedicated to the widgets. I just wanted to kind of make us all aware of some of the different plot types that we have available to us within Pandas. So here I've got a data frame, and the way I'm accessing it is, again, plot. And so we went a little bit over the group by method yesterday: split, apply, and combine. What I'm doing here is I'm just taking every column and I'm applying this method from pandas. So this is a lot to unpackage, but basically I'm just creating data for us to plot with a bar plot. I'm taking the average of every column in our data frame. But the thing to note here, in terms of plotting, everything is the same, except now I have this keyword flag within plot where I'm saying make it bar H. That's a horizontal bar plot. And then this should look familiar. I'm saying send this to my axes object that I've established earlier in the code block. I'm actually curious. Let's look at what this raw data output looks like. Right, so we see we've got each one of our columns with the mean data value of the data associated with it to its right. And I'm just taking a plot of this. If I want just a vertical bar plot, I can take away the H. Now I've got a vertical bar plot. This is so much easier to route through pandas to make plots like this of categorical data than it is to try to build up from scratch from matplotlib. If you try to build it up from scratch from matplotlib, you'll be finding yourself having to make your own legends, make your own colors, all this sort of stuff. And in this way, pandas will automatically determine, do I need separate categorical colors? Do I need a legend, etc. And at the end of the notebook, I have a little bit more on creating bar plots through matplotlib. So another important plot type for statistical analysis are box plots. I have a little link here to the box plot API. For those of us who might need a refresher, this plots the mean or median and the interquartile ranges. Outliers are plotted as little dots that are outside of our 3 sigma, I believe. I think it's anything outside of 3 sigma. I think it depends on what box plot, what type of box plot. I think there are different versions. But you can read more about this in the box plot API. Just know that outliers, however we statistically define them, appear as circles. The range that is associated with how we define those plots is these little tick marks that are above and below. And then our interquartile ranges of the blue and our median is the green. There are different flags you can do to plot both mean and median, things like this to kind of add more information to your box plot. Something that's like not awesome about this is I've had to write a whole bunch of code to make this appear horizontally. I don't think that there's like a horizontal box plot that you can use out of the box. Yeah. So you're going to be stuck with seeing these in this fashion without kind of writing a whole lot of other code. Again, the default behavior without doing any kind of group by or apply method to our data frame is to just segment things by their columns and associate the data like this. Another important data graph type for data analysis is your histogram. We have access to this. I don't know why I did it this way. Let's so in this case, I did it directly with matplotlib. I don't think this should pose any problem, but let's go ahead and do it down here. df rad dot plot kind equals hist. So should be able to do it both ways. kernel density estimates, or KDEs, super useful. If we're not familiar with them, you can think of these as being extremely similar to a histogram, but instead of determining a bin size where we just deposit counts of where our data appear, we instead just deposit a Gaussian distribution around the exact point at which that data appears. So folks often really like these because we're not hiding behind any assumptions on how our data should be binned, right? I'm not confining my visualization to predetermined bins that I've kind of ad hoc determined, right? So folks really like KDEs for just getting a much more clear, non-biased understanding of how the data is distributed. So it's a really important plot type to be familiar with. And again, you should start what's fabulous about this is the API for these are all very similar. I've got my Pandas data frame selecting a specific column, doing plot, and then the kind parameter will determine what kind of plot I create. You know, I actually haven't tried this. Let's see what happens when I just plot the whole thing. Pretty ugly. Let's go ahead and play with this for a little bit. I'm going to do ax.setXlim. Look at that tooltip. That tooltip is very nice. So it's telling me what I have access to. I'm going to say I want my X range to go from, I don't know, -1 to, well, I don't know, let's do 100, right? Like what we did in our exercise earlier. So you can kind of see how like this is actually looking. Let's like take it down to 20 now. We're starting to actually kind of see those curves. Again, these distributions are so dissimilar that it's a really messy thing to put into one plot. This is where you can start to kind of think about, you know, top level, how should I parse this data? Should I put this into one visualization? Should this be separate? In this case, I think these should definitely be separate. This doesn't really look very, can't really take a lot out of this, right? In fact, it's so awful. I'm going to change this back to what it was before. Okay, so this is fun. So tomorrow we're going to talk about like regressions and making basic models of our data. And I thought this would be like a very poignant, I don't know what poignant means. I'm going to go ahead and use it because it sounds right to me. I thought this would be a very poignant example to go through with visualization. So correlations between our input variables. Not going to talk about those equations, but you know, if you like, you can go and peruse StatQuest. I thought these were very helpful. What's his name? Starmer. He actually is on Spotify. He like has his own music. So he's got a good sense of humor. It's fun to watch, but he does a good job of explaining these. Basically, if our correlation is positive, our variables are positively correlated. If it's negative, they're negatively correlated. The closer it is to 1, the more correlated it is. -1, the more negatively correlated it is. 0 is there's no correlation. So, tribute to Pandas, again, great functionality right out of the box. I'm just going to do df.core, and I generate this matrix of Pearson's correlations between all of my variables. This is a lot of information to take in. And this is going to signal us that we need to think out of the box when we think of how to visualize this. So great work has been done here on data like this. What we're going to do is apply a heat map to this matrix to kind of quickly ascertain where our dominant values are in terms of very highly negative or very highly positive. This was the one cell where I thought I let NumPy continue to lurk. As we found out, there's actually in other places as well. But I used a nifty trick to basically cover up this top half of our correlation table because it's just a repeat of the bottom half of our correlation table. If I were to make this chart out of the box, let's do this. The other thing that I'm leveraging here is Seaborn. Seaborn's heat map is very nice. So let's do this, get rid of that. And I'm just going to feed it my matrix and see what it does. So what it looks like out of the box, right? Not bad. All I've done in the cell below is I've applied my white mask to get rid of this redundant information in the top right quadrant. quadrant's not the right word because there'd be 4, right? It's the top right half, I guess. And I have changed the size and I've changed the color palette to another seaborn color palette. But the takeaway here is we want to get rid of redundant information. We never want to have redundant information, you know, as little as possible. We want every single thing that's appearing on our visualization to mean something, to have a purpose. Treat this like valuable real estate. So we've gotten rid of that upper half of our heat map. All right, so we're thinking tomorrow we're going to make some models about this. We're kind of interested in how things are related to each other. And so I'm looking at this, I'm just looking at what variables are highly correlated. I see that on the positive side, I've got NOx, well, I guess it was nitrous oxide. What did we talk about? I don't remember. This NOx is highly correlated with industry, INDUS. I don't know what these mean anymore, but
yeah,
that's okay.
It's
nitric
oxide and then the amount of space that's in zone for industry.
Cool. So that we also have tax and RAD highly correlated. And so let's say I just wanted to like start looking at this for myself. I'm gonna go ahead and come down here. Kale, that's a good question. I'm actually not sure. I mean, it's possible, but I don't know if it's going to be neat. You can plot text over any figure. You have the ability to do that. You can tell it the actual like XY pixel location and say put this text attribute here. So like in the most kind of messy sense, you could create a for loop that iterates through like those locations in your matrix and plots the actual label value. You could do that. But a better answer is I don't know if Seaborn has the ability to display those labels or not. I'm not sure. The API might tell us. Thanks, Dave. So let's say I'm just looking at those correlations now. I'm like trying to say, I'm looking at and saying, I want to see the data for myself, right? And so down here, I've plotted RAD versus TAX. And I'm seeing that, yeah, there's kind of a positive correlation, but I also see that there's these big outlier values, right? That could be sort of persuading my single digit summary of that relationship in a very overpowering way, right? So this is an example of how we would like to look at summary data, but then to be able to drill down and see for ourselves what is influencing that single summary value, that single statistical summary of our data. I'm going to iterate through a few more. So DIS and age are negatively correlated, so I'm going to look at that. That looks a little more reasonable. I see that like a lot of my data is highly concentrated in the low range for RAD and the high range for TAX. So this correlation may not apply for certain ranges of data, but we do see like a general kind of negative correlation between the two features. Let's do one more. So another one I see. I don't know, tax and Indus. Sort of a weak positive correlation there. So what I'm getting at here, what I'm trying to motivate is as we do this interaction with our data, as we're iteratively exploring the different variables that we're interested in, it can be very taxing to go here and code this by hand over and over in the same code block. So this is where IPI widgets comes in handy. There's a lot of cool. I actually don't know how a widget is defined. It's like a thing, like a non-coding term. Widget's just like a. Anyway, there's a lot of cool widgets in IPI widgets for us to use. I'm just going to talk about one that works really nicely out of the box, interact. So the way this works is instead of just declaring a figure axis object, I'm going to write them inside of a function. right? So in this, I'll talk about the input here in a second, but let's just go through the insides of this function real quick. So I'm making my correlation matrix. I'm calculating the I'm using splicing, or yes, splicing to access the Pearson's correlation value I'm interested in. I'll talk about this in a second. We're not actually using this in this example. I make my figure and axes, standard that we've seen all throughout the tutorial, and then I'm plotting my target value, hard-coded in, and then my y value. I'll show you that y value in a second. So on my x-axis, if we're just looking at this, my x-axis is always going to be my target. And my y value is going to change depending on what I select in this drop-down menu. So now I can kind of quickly go through and just play with different things that I want to look at one at a time. Oh, that's a good one. Rooms versus target value. The rooms in your house, the number of rooms is highly correlated with the value. Is that what that's saying? The age, sort of negatively correlated unless it's really old. So what's happening is this y field that I defined in my function, what have I fed it? I fed it whatever this is, df.columns. What is that? It's a list. We're going to call it a list. In simple terms, it's a list of all the different columns I have in my data frame. And so what interact does is it turns that list into a drop-down menu for me to select. And then because I've defined that variable as y, as I run my code down here, my y value in my ax.plot command is being replaced by what I've selected in my drop-down menu. Right, and so I've got a kind of a simpler example down here of what's going on. If I weren't to use this with interact, I would declare my y parameter is just a string, because that's what I need to select the column that I'm interested in. And then I do plot, and I just plot that same y value every time. Yes, great question. That's actually what we're going to do. So our next exercise is to add oh, Wes. Well, so my code block here gives you kind of some pseudocode that I didn't mean to go that far. You can look at that if you would like, or you can ignore it, and you can just look at the actual code block. But the objective here is to not just feed in an x parameter, but a y parameter as well. So I'm going to give us 5-ish minutes to play with this, and then we'll come back.
Wes, you just got a nice question in the chat.
Yeah, from Emily.
Yeah.
Yeah. So that's what we're. So let's see. Yeah. So that's what we're doing in exercise 5. So the answer is yes. Yes, you can. And I suppose just to reiterate, previously, a couple minutes ago, we had declared an input parameter field y. And we had fed that parameter field a list that we generated using df.columns. We hard-coded in our x values as the target values of our data frame, right? And we see that here, df target. So what we'd like to change in exercise 5 is to also have the x field as an input to our function, myplot. And then we'll call that function myplot in the same exact way as we did before, just interact myplot. And if we have extra time, we're going to write a descriptive docstring to describe what our function does. And as we're working on this, maybe some of us have completed it. We're sitting in silence and Wesley isn't talking, thinking about what are some other useful input fields for something like this. You know, I'm thinking about that really ugly histogram from earlier. You know, I was changing my x-axis range by finger flapping. That would have been a nice field to have like some kind of iffy widget to filter for.
What if you have a really old PI and you have to increase the size of your fonts? What would you do in that case?
You have control over that. There's actually, ooh, what did I just do?
Oh, wow.
I just like
Well,
jumped through cyberspace. So to answer that question, I want to go back. Where was I? Okay. I think I did what Dave was mentioning yesterday. If you're not like in a certain place and you click B or A, it'll take you over into Netherlands. What we noticed with this, and I'm just going to do some stuff. What do I want to do? NP range. Actually, I had some X and Y variables stored from earlier, don't I? Can I just do this? Ugh. Okay. All right, Stephanie, let's look at this. So we have this default, right? And we see there's like a ratio. We can look at our font sizes there. If I make the figure bigger, so I'm going to do fig size 10 by 10, our figure gets bigger, but our font sizes stay the same. So this is something to think about. So you can make the figure bigger, and then to make
you can do it from like the X label. You can set font size in there. So if you have like, yeah. I think it's just font size. You have to literally type font size, the keyword.
Is it font size?
Yeah. And try increasing that, or like scroll. I can't see your X, what it looks like, but.
Well, set.
But you'll need set X
Are you
label.
trying to make the
X
labels or the ticks bigger?
Oh, the text. So it's not, I don't think it's set X label, it's just.
So right now there's no X label. If you wanted to make the ticks bigger, you do set X ticks, I want to say, and then font size 10.
You're right. High five, Evan.
So it's like, what does 3.2 do?
I think you have, if you want to set your actual ticks, you have to give it like a list range with like all your ticks, which becomes a pain. But if you just want to change the font size, then I think in your set X ticks, you can just change not size but font size. Yeah.
I think,
Okay.
yeah, the takeaway for me here is there's like the APIs, or you have to read a little bit about what it wants, but all these things are adjustable. I don't remember out of the box. Minor equals true. What does that do? Yes, can IPI widgets help me select from continuous values rather than categorical values? I believe there are widgets where you can have text box as a field and you can type in whatever quantity, whatever float value you want. But other than that, like if you were to use like a range slider, I believe you're forced to quantize them to some, they have to be discretized to some frequency level step value. Thanks, Sir Ryan. Oh, where you got X? There we go. This is like, it's like Stack Overflow has become the chat, and I'm just gonna like cycle through these. Sweet. All right, let's do this. 120. Dang, son, look at those bad boys.
Those are humongous.
Gnarly.
You can see them from
Humongous.
here.
Hey, Stephanie, can you see those? Can you see them?
Wait, let me check.
I can hear them. They're so big.
Yeah.
This has just become Sesame Street.
I was just putting in the chat, like if you want to update all of them, like your ticks, your ax labels, and so on, you can, right after you import matplotlib, you can set your REC param for all your font sizes.
Mm.
And I think what I typed wrong, there's like a dot in there that shouldn't be there.
Hey Wes, you just mentioned Stack Overflow. Can you talk a little bit more about that for a second?
Yeah, well, I learned something yesterday from your tutorial, and that was that error messages were called stack traces. Did you say that? Did I like?
No,
Okay,
that's right. They're called stack
traces.
traces. Yeah.
I don't think I knew that.
But like, if somebody wanted to look up some of these matplotlib things, how can they use Stack Overflow to do that?
I literally go, how to make matplotlib ticks bigger. And Stack Overflow is, so this is the thing about, internet bubbles. I don't know how much of Google is because of the way I use Google and it remembers what I click on, but my first results are typically Stack Overflow related. And then similar to how I used to like study answer keys in college, I don't read the question, I just read the answer. It's usually within a few seconds you can get if someone's actually got a good answer for what you're looking for or not. So, and it's usually like the most upvoted, but sometimes like for various reasons, like the accepted answer is further down. Like in this case, I think this guy got more votes. Label size. Rotation is another useful keyword. They're using it for their ticks. I don't know. That's probably useful, but particular for your labels, oftentimes, like if you've got a bar plot and it's categorical and you don't want a legend, you want these labels, having the rotation keyword is super useful. Anyway, I do use Stack Overflow all the time. Okay, so I want to take us back. Exercise 5. I'm gonna see if I can crunch this real quick. So we saw this before, right? Y equals df.columns. I'm just going to do it the same thing as for x. I'm going to write my doc stream. Quick note on doc streams. I really like mimicking sklearn for these. So you usually have like a general description, say some stuff, and then you have parameters, and then you have some dashes, and then you say X, and the type is a list, and then tab into that, you say default value is the first item in the list, some other stuff that you can want to say about it. Same with Y, list, description of Y. And then you want to say returns. And then you say fig, whatever you're calling your returns thing. Matplot lib figure. And then a description of it. So yeah, so Dave's got it in the chat. sklearn is really great. If you there's a handful of packages out there that will auto format your doc streams into online documentation for you. So Sphinx is a major one, and if you format your doc streams this way, it will make it really nice looking for you. So what's an example of that? Read the docs.io. So if you host it on here's like where
impedance.py might be a good one.
Impedance.py.
Yeah.
All right. I don't know how to do this. Oh, I'm going to show you guys my package. That's what we're going to do. Wait, is it there? Did it disappear? This is my grad school. Where is it? I guess it's not there anymore. It's super sad. Is there like a search bar on this? Okay. I don't know if it's, there we go. Look at that bad boy. So what it does is I can go to, what's the actual formatting? Man, sad. All right, we've gone down this gravy chain long enough. Where was, I don't know. I just want to see some functions here.
I put a link for impedance.py into the chat, and then if you go to the fitting
thank you.
part, yeah.
Yes. Nice. Okay, this is exactly what we're talking about. So if you format your doc streams like this, these APIs will format them and host them for you in a nice, clear way. So there's a whole ecosystem of this sort of thing. Okay. Where were we? All right, so we're writing our doc stream. We're done with that. I have my X and Y. Here I'm putting Pearson's, plotting X and Y. So I think that should work. Let's test it, interact. My plot. Okay, I've got X and Y. Cool. So, you know, really cool, like easy to use functionality with IP widgets right out of the box. We're right at I don't know time anymore. I think we're at 1 hour 45. So we're just in time for the breakout session. We're going to take this idea. We're going to continue with this idea of making an interactive visualization. And the idea is when I have these disparate X and Y dropdowns, and if I'm interested in how things are related to one another, how they're correlated, this can be a really cumbersome way to kind of tease out that information. And so I've got an advanced exercise for people who would like something a little more challenging, where you go and you make the drop-down menu yourself. You have to use a lot of Pandas logic for that. In the basic version of this, I've provided that. I'll walk you through that in a second. But the idea here is, instead of having separate menus for X and Y. Our drop-down menu is a list of XY pairs, and it's sorted by the absolute value of those correlations. So when a user goes to interact with your visualization, they now have a smart drop-down menu that procures the most sort of salient information up to the top. So they're not kind of getting lost in the weeds looking at spurious correlations between variables. The bonus for this is if you have extra time, play around with subplots, see if you can populate other axes with interesting information about those two variables that are selected in the drop-down menu. In this case, I did KDEs. I'm not going to walk through the logic for this. Some of it's a little bit advanced, but I want to share with you the end result of it, and that is this data frame. And so if you look, I've got a column that is my first feature, a column that is my second feature, and then a column that is my Pearson's correlation between those two features. And my index, right? Yesterday we saw just an index from 0 to 1 minus the data frame shape value, right? I've replaced that with string values that I want to use as labels to my drop-down menu. So the objective in our breakout is to make our figure again, this time with the index of this data frame as our labels in our drop-down menu, right? And the data that's returned from that selection to set our X and Y variables to then access the data from our original data frame to plot.